If you're ready, switch screens and make you presenter.
Okay, sounds good.
All right, everyone, enjoy your session.
Okay, so today we're going to be talking about moving big data. Specifically, this session's focused around a lot of the beginning pieces of working with big data, specifically the Hadoop file system and the Hive database, and some of the means that we as SQL Server professionals can use to move the data in and out of those systems and integrate it into our SQL Server systems. So that's what we're going to focus in on today, and I will get started with the presentation as soon as my mouse starts responding. There we go. Okay, so just a little bit about me. I work with Pragmatic Works. I actually manage the
John, I'm sorry.
side of the Pragmatic Works business.
We can't see your screen.
Okay. That's interesting because it is showing it.
Oh, there we go. Now I can see it.
No,
oh,
sorry.
Now it went back, actually.
Sorry, about the same time you said that, I told it to stop sharing. So
okay, perfect.
Hopefully it's back up now.
Yes, thank you.
Okay, good. I apologize, everybody, for the technical issues here. This laptop has worked fine, and I'm going to blame it on Microsoft. So, okay. So, work for Pragmatic Works, managing the software group. We basically work on a lot of products that extend the SQL Server family of products. My background is in doing business intelligence consulting. So I've been looking into big data over the last couple of years, primarily is to understand the space and the level of interest out there in it, and getting familiar with it as it applies to a lot of the business intelligence initiatives that are going on. So when we talk about big data, one of the first things you'll notice is there are a lot of different definitions of big data. When people say this, they can mean a lot of different things, and big data does mean different things to different people. But when we talk about it, particularly coming out of the SQL Server world, what we really mean is data that can't be managed in a traditional relational database. So some ways that you're looking at data that can't fit into a traditional SQL Server are some characteristics known as the 3 V's. So we have volume, velocity, and variety. So volume, we're talking about the amount of data. So one indicator that you're not dealing with big data, there's a story that was relayed to me by a consulting friend who went into a customer. They had requested that somebody come out to help them with the big data problem they were having. And when he went into the initial meeting, they handed him a thumb drive and said, "Here's our data." And he said, "Give me a sample of your data." And they responded, "No, that's all of our data. That's the big data problem that we're having. If your data fits on a thumb drive, it is not big data." So you can use that as a pretty good rule of thumb. When we talk volume of data, we're talking generally, rule of thumb here, 5 terabytes and up before you're really talking about a big data type of volume. Under 5 terabytes, and you might have to buy some expensive hardware, but you can usually manage that size of data as a single data store inside of a traditional SQL Server or other relational database engine without having to move to really a big data structure. Using things like PDW, the Parallel Data Warehouse that Microsoft's come out with, that's kind of the top-end SQL Server implementation. You can actually scale well beyond 5 terabytes and still keep things in a relational database. But it does require specialized hardware, and it's a bit of a different process. So Parallel Data Warehouse is a big data solution the same way that Hadoop is a big data solution. They just address slightly different methodologies for how to work with that big data. So again, volume, we're talking 5 terabytes up through petabytes of information and even exabytes of information. to really qualify as a large volume for big data purposes. High velocity, what we mean here is the data is coming in so fast that a traditional relational database system just can't handle the load. So this is where, perhaps if anyone in the audience is working with manufacturing, you have assembly lines. Assembly lines have sensors on them. Those sensors can report, thousands of bits of information every second in some cases. So collecting all that information tends to overwhelm a traditional SQL server, primarily because SQL Server is limited to running on a single node for the most part. And yes, there are scale-out solutions with SQL Server, but they tend to be a little limited and require things like replication, etc. So if you're looking at the traditional, I have a SQL Server, trying to funnel that much data into it over a very short time period tends to cause some problems. So when we talk about velocity, those are the types of scenarios. We've got hundreds to thousands of transactions occurring every second, millions of transactions over the course of an hour. Those types of things tend to start pushing us more toward a big data type of solution. And then the final V is variety. So what does this mean? A lot of you have probably heard the term unstructured tossed around quite a bit when discussing big data. Unstructured is a little bit of a misnomer, but we'll talk a little bit more about that in a couple of slides. But what people usually mean when they say unstructured data is they don't have a precise definition of the structure when they're collecting the data. So this could be, I'm collecting web logs from a variety of web servers. Some of them are implemented with different technologies. Some of them are on different versions. So their logs all have slight variances in how the data is captured. We don't have to worry as much in a big data solution about the different formats and structures of the data. We're allowed to more easily capture the data up front and then apply some of the formatting on the back end. So that's the third V in this equation. So some examples of this, some of the more impressive ones that I've run across in my research. Everybody's probably familiar with the Large Hadron Collider that is threatening to create black holes and consume our universe. So far it hasn't done that, so that's a good thing. I haven't checked recently, but I think we're still fairly safe. The interesting thing to me about this is these are creating situations that occur in the fractions of a second, and they have a huge amount of sensors to try to collect all the information that they possibly can about these interactions that they create within the collider. Well, right now they can produce basically the equivalent of 25 petabytes per year of data, and that's running their sensors at 1,000% of what they're actually capable of collecting if they had a way to store all the information. So you think about that, that is a huge volume of data coming out very quickly. So it meets both the volume criteria for big data as well as the velocity data. Another example, Walmart, I'm sure all of us have shopped there at some point. They do millions of transactions an hour. They are collecting all this. They're doing basically very close to real-time analytics on top of it, and that's all enabled by big data systems. And NASA has 32 petabytes of climate data that they've recorded for the last several years. So if you think about trying to even store 32 petabytes of information on a SQL Server system, it kind of boggles the mind to do that. Apologies. So another great example of kind of a big data usage that I found particularly impressive. There's a cell phone provider in Japan that actually tracks, this can be a little scary if you've followed along with the recent NSA revelations, but they actually track their customers via the GPS. Hopefully this is an opt-in thing and not just something that they do. And they give out awards basically to the customers who walk the longest distance in a given month. So they're actually, every time that a Customer, basically their phone checks in with one of the cell stations or cell antennas. They record their position and they track that. So you're talking every subscriber to this particular company in an entire country. It's, again, a huge volume of information that they have to capture and then be able to do analytical processing on it. Another kind of interesting, also somewhat scary example, here in the United States we have the CDC, the Center for Disease Control, and they are responsible for tracking all sorts of information about health. One of the things that they do is look for flu outbreaks. So currently they do this by collecting information about doctor's visits, the types of prescriptions being written in different areas, reports filed by doctors, those types of things. So they're generally able to identify that there's been a flu outbreak in a particular geographic region within about 2 weeks of it actually happening. So 2 weeks after it starts, they can tell you, yes, there was a flu outbreak here, it's confirmed, and start taking preventative action. Well, 2 weeks is kind of a long time for a flu outbreak. It can spread to quite a few people in that amount of time. Google is actually able to, by all the work or all the stored searches that they've been able to collect over the years of everybody using them, they're able to run analytics on that and identify patterns in searches. So using that information, they're able to identify flu outbreaks within about 6 hours of it starting. And they do that basically by saying, in this specific geography, there's been a lot of searches for these specific terms, things like fever, flu, etc. And it's in a small enough geography, and we're seeing a big enough spike in the number of searches on this that it matches the pattern of flu outbreaks we've seen in the past. Thus, we can fairly confidently predict there's actually a flu outbreak going on right now in that particular region. So by leveraging that, they're able to do this so much faster. It's still, in some cases a little scary that companies are collecting this amount of data and they're able to do these things. But to date, for the most part, it gets used in the aggregate. So it's not quite as big of a privacy concern, but certainly there's more and more focus over the last couple of years on how to use this type of large patterns that they can identify to more reliably identify what individuals are going to be doing. For example, a lot of police departments are now using big data to look at historical crime rates, historical crime areas that have high crime, and predictively send their officers out to those areas in advance so that if something happens, there's a policeman already nearby, or that they can actually prevent the crime just by having the police presence in the area. So if you've ever seen Minority Report with the pre-crime that they talked about there, we're definitely heading in a direction for that, which again, it's a little scary in some respects, but at the same time also from a data professional standpoint, a very interesting use of the data that's out there. So I mentioned unstructured a little bit earlier. So one of the buzzwords, particularly from kind of the management level, you tend to hear about big data is, oh, it's great, we can put all of our unstructured data into the big data system and we don't have to worry about it. Well, unstructured is really a misnomer for this type of information. There is structure to the data. It's just, it's not uniformly formatted. So when we talk about big data systems, the big difference is, when do we apply the structure to the data? With the SQL Server, we submit information to it, and SQL Server won't accept the information unless it conforms to the schema that we defined up front before we even got any data into the system. So when we define the table, we tell it you're going to have 10 columns. 5 of these columns are marked as not null, so we know they have to contain value. All of the columns have a data type on them, so they have to be a varchar or a date time. If they are a string column, we know how long that string is supposed to be as a general rule. Of course, you can use in varchar max and things like that to work around that. But typically, the data and the rules around the data are very precisely defined up front with SQL Server. Even to the point of being able to have check constraints and other things that check the data, ensure it's valid according to the business logic before it's even recorded to the database. Well, the big data approach is to turn that on its head and basically say, we don't really care what you're putting into the system. It can look like anything. We're not going to check to make sure it conforms to any given structure when the data is put in. What we are going to do is apply the structure when the data is read back out of the system. So this is basically when we read information from the Hadoop systems, then we would tell it, okay, I expect that when I tell you to read this particular set of data, that what you're going to return is going to consist of 10 columns, and I expect this column to be a string, I expect this column to be a number, etc. And then the tools that you work with on top of Hadoop handle taking whatever's there and attempting to translate it into the format that we specified. So again, in something that's a little different from the way we think about things from a SQL Server standpoint, rather than failing, as an insert would fail if we tried to put data into a SQL Server table that didn't conform to the schema, when we try to read data out of a Hadoop system and the underlying data doesn't conform to the schema that was specified when we read it out, basically it will return with null or blank or whatever the default value is, rather than failing. So it's a much more tolerant system of having data inconsistencies and things, which again, if you're a data professional working on SQL Server, it can be a little hard to kind of wrap your head around that type of flexibility in the data that you have. But it's very valuable, and one of the things you have to keep in mind is, again, we're talking, large amounts of data. So if you're processing a terabyte of data to look at customer buying patterns, if 5% of those records have bad data in them, is that really that big of a deal? Well, again, as long as as you're not doing bank account processing or something like that, where each individual transaction actually matters, then you can do a lot of interesting predictive modeling and those types of things off of data that does have some inconsistencies and does have some problems. And that's really more the types of solutions that are being solved with big data today, is that type of more flexible underlying data sets. You don't see a lot of systems using big data to do again, bank account transactions or something like that, where each and every record really does have to be precise and conform to an expected set of values. Okay, so a quick overview of the Hadoop ecosystem. This is not a complete picture by any stretch of the imagination, so this is some of the simplest or a very simplified view of it. Hadoop is open source, so it tends to see a lot of development that goes on, and people in a lot of open source communities tend to work on the stuff that interests them. Since in many cases they are either donating their time, that it tends to, you can see a lot of divergence in the type of things that are, the technologies that are produced. So there are many things that work in the overall Hadoop ecosystem. This is just focused in on a few of them. So underlying the whole thing, we have the HDFS. HDFS is highly distributed file system, Hadoop distributed file system. It also is a highly distributed file system, but the H is for Hadoop. Basically, this is a file system that is optimized to run across an entire array of machines. So rather than how we probably think about it with our typical Windows box today, where the file system is based on a hard disk that sits inside of our computer, or perhaps something specifically allocated to our machine from the SAN. In a distributed file system, the actual chunks of the files are located on many different computers that are spread out over every machine that participates inside of the file system, or the cluster is the term that they use from a Hadoop standpoint. So for every machine in the cluster, it has some dedicated storage to the file system, and this allows files to be, again, stored across many different machines. It makes the file system very fault tolerant if you have replicas of your files, and we'll talk more about that in a little bit. But it also lets you distribute the workload out of actually reading and writing those files. Because they are on so many different machines, then you can actually do the processing of the files on all those different machines. So it makes for a system that can scale out very easily. On top of that, on top of the file system, we have MapReduce. MapReduce is a technology that basically takes things that need to work with that data, splits it up into smaller chunks, and actually runs the processing on it. And I'm not going to spend a ton of time on this because we have a slide on it in just a couple of, about 2 slides. So on top of MapReduce, so again, MapReduce, just to re-summarize that, does all the heavy processing of the data in the file system. On top of MapReduce, we have 2 technologies that we'll talk about today. We have Hive. Hive is a tool that makes your data in your Hadoop file system look like it's coming from a relational database. It's not a relational database, but you can work with it using select statements and things like that. So it is a little bit more of a traditional experience. One of the pluses with this is it enables a lot of tools that already work against traditional databases to work against data stored in Hadoop, because they can simply query Hive for the information in the same way that they would query a SQL server. Pig is another tool. Pig is more for data transformation. Both Hive and Pig get used for data transformation pretty heavily. Pig, to me, feels more like an ETL type of tool, whereas Hive feels more like a tool for easily querying data. Both of those sit on top of MapReduce because basically what they do under the covers, when you submit a request to either one of them, they will create a MapReduce job to do the actual processing. HBase is a NoSQL database. So if you've heard of NoSQL, excuse me, basically NoSQL means a lot of the traditional relational integrity concepts that we're familiar with from relational databases, such as enforcement of foreign keys, things like atomic transactions aren't enforced on a NoSQL database. So it's supported that one, and actually doesn't need to use MapReduce. It basically goes straight to the file system. And then finally, on top of all of that, we have hCatalog. So this is basically a metadata system for the Hadoop ecosystem. It lets you say, okay, I've got all this data stored in my Hadoop file system. What does it actually look like? What are the different ways that I can get to it? So it's an attempt to start putting some of that structure on top of the Hadoop system so that you can query it more effectively. So this is what a Hadoop cluster looks like. Basically, you have a name node up front. The name node acts as kind of a controller, and it is basically the single point of failure in a typical Hadoop cluster. If the name node goes down, nothing else can interact with it. The data nodes, on the other hand, are typically redundant. So you usually won't have more than one data node for reasons we'll cover in just a second. But if a particular data node goes away, it's usually not a big deal because the data any data node stores is replicated across other nodes in the same cluster. So what you'll see in a lot of environments, the name node is put on safer hardware, where you have built-in redundancies like multiple power supplies, multiple NICs, etc., so that you have a better uptime guarantee with it. Because again, it is kind of the one point of failure with the Hadoop cluster. The data nodes, on the other hand, those can go away and you can just replace them. They're not nearly as critical. Oops. So the way this works is that when we have a file come in, basically the name node says, okay, I'm going to place this file on a particular data node, and at the same time it will automatically create multiple replicas of that. So it actually chunks up the file into multiple blocks by 64 megabytes by default. So again, we're dealing with large files here, single kilobyte files, typically not something that you can store in your Hadoop file system. It takes those, chops them up into multiple blocks, places them on data nodes to make sure that you don't have replicas of the same block of information on the same data node. And then when we want to submit a MapReduce job, it can take that and basically say, okay, I know this file has been distributed across these 3 data nodes. So I can take the MapReduce job that's coming in and also distribute the processing for that across 3 data nodes, the same 3 data nodes that have the data. So the idea here is, instead of what we would do in a traditional SQL Server environment, we're processing data in an SSIS package as an example. We might pull the data back to the machine running SSIS, and we're doing the processing using the local resources of that machine. We're using its hardware, its CPU, its memory, etc. And we incurred a cost there of actually pulling the data back across the network to that machine, doing the processing, and then sending the data across the network again to wherever it needs to live. The idea behind Hadoop is kind of the opposite of that. Instead of pulling or moving these potentially large amounts of data, terabytes plus of data, across the network to a single machine and consuming all of its resources to do the processing, let's split that up and let's send the job itself out to all these different nodes so it can process smaller chunks of data. We don't actually have to move the data. And then, since a lot of this processing tends to be aggregating results up, we can take the results of each individual chunk of work, combine those together, and return the final result. And it's a lot more efficient than having to move all that data around. So that was basically the philosophical approach they took with it, and it's a good way to think about how MapReduce works. Okay. So that was a kind of quick introduction to the Hadoop ecosystem overall. Again, big things to remember. Data structure is applied when we read from Hadoop, not when we write to it. So as a general thing, Hadoop just looks at data you're storing in it as being files, and it doesn't particularly care what's in those files. What it does care about is when you try to retrieve the data out, that it can retrieve it, and it will do the best job it can of translating whatever's in those files into the structure that you requested from it. So we're going to talk about 3 options for interacting with Hadoop data: integration services, Sqoop, and Pig. So integration services, if you've been in the Microsoft space, you're probably already familiar with. The way that we use it when we are working with Hadoop is typically via Hive. So I already mentioned Hive looks like a relational database, and it lets us query information in Hadoop as if it is a relational database. There's a couple of things to bear in mind with this. So we use the combination of Hive plus an ODBC driver to do the querying. It does not support writing back to the Hadoop server, though. And the reason for that is Hadoop is basically a write once, read many file system. So there's not really mechanisms in place today to handle updating files in place. If you want to update information, then you basically replace the file that contains that information with a new version of the file that has the new information in it. So there's not really an update model built into Hadoop. It's really intended more to, I'm going to write the information out and then I can query it as many times as I want. So when we want to write to Hadoop from Hive, we have to go through a slightly different path. So let me show this real quick. So we have a couple of SSIS packages. Sorry, my bar is getting in my way here. And first, let's look at an extract from Hive. So this is the simpler case. And it is complaining because it can't see my Hadoop server. My apologies. I had to reboot immediately prior to this, and for some reason it is complaining that it can't actually connect to my Hadoop machine. My apologies. I won't be able to actually demo the moving of the package. This normally works great, so I'm assuming just something to do with the reboot process. But the way this would work. You're going to set up an ODBC connection manager. In this case, the ODBC connection points to the, what I'm using here is the Hortonworks distribution of Hadoop. So that's one that's actually optimized to run on Windows. They also provide an ODBC driver, which is what this Hive demo DSN is actually pointing to. From there, we can just simply use the SSIS ODBC source, so nothing special about this, and we can run standard SQL statements, select star from, table name, using where clauses, group bys, etc. All of the traditional syntax for running against or for selecting from tables is supported by Hive. So we can use that to actually query the data and get our results back, and then simply in this case we would write it to a SQL Server target. So that's how we would get data out. Again, pretty standard extract process from an SSIS standpoint. To load data in, as I mentioned, a little bit more complicated. So I've found that one of the best ways and one of the fastest ways to get data into Hadoop is write the data that you want out to the text file format that you're using in Hadoop. And then just copy that directly to the Hadoop machine and then call commands on it to put the data into the Hadoop distributed file system. So basically the process here, I've got a bunch of text files that I already laid out that are what we want to process. Those are in a directory, which this for each loop container is basically processing. It's capturing the file name in a variable. I use a file system task to actually copy the file, and the target location is actually a network share on the Hadoop machine. That's stored in a variable that you can see here. And then I call an execute process task, and I'm calling a process that is the sysinternals psexec process. So psexec lets you execute processes on remote machines. So because I'm using this, I can actually call the server that I'm looking for. Let me actually make this a little bit bigger, and then I'll zoom in. So I tell it the server I'm looking at, I tell it the path to the command file. So I want to actually run the Hadoop command file and tell it to do a put command. So put basically is the command you use in Hadoop to say, copy this information from my local file system into my Hadoop file system. So I grab the information from that same location, the UNC path, and I copy it into my moving big data folder on my Hadoop file system. So there's a couple of advantages to this. One is because I'm using the psexec, I don't actually have to install any of the Hadoop components on the machine running SSIS. The only thing that I need on here is the ODBC driver, and that's purely for retrieving information. So this lets me kind of get the data up there. It also tends to be fairly fast. Hadoop loves text-based data. So I can create the text files using SSIS on my machine and then publish them to Hadoop this way with kind of a minimum of fuss. So one comment I will make about psexec, security can be a little finicky with it, so you need to make sure that the account you're running the SSIS packages with actually has the required permissions to execute the psexec command that you're calling on the other server. Okay, so let's switch back to our presentation. And just to recap the SSIS piece, again, reading, fairly simple, follows the same model you use to read from any database. Writing, a little bit more complex. Excuse me. But still using the text-based file and the psexec approach. It's not too terribly complicated. Sqoop is basically the import-export wizard of the Hadoop world. So this is, again, one of those pieces that's an open source project that gets distributed alongside the Hadoop environment. So Doesn't help you a lot if you need to transform the data, but if you just need to quickly copy data from one location to another and the data already looks pretty much like you need it, it works really well for that. So you can go use this to go from Hive or direct from the HDFS file system. Again, doing major modification of the data, probably not, but if you just want to export something from your Hive database to your SQL server, it works really well for that. So let me find our script here for this. And this does take a few minutes to move, so I'm going to kick it off, but I'm not actually going to run the whole thing. And I am hopeful that this is going to work. The issue I was getting earlier was indicating that my Hadoop machine is not visible to my SQL Server machine, which probably means the reverse is true as well. So this may error out on us right away. But just to show you the syntax, basically this is going to move information from our SQL Server. And while this is running, I'm going to switch gears back to this. We're basically connecting to a SQL Server. We're using JDBC here. So again, Hadoop is primarily written using Java. Most of the components and the things you'll use are going to be Java as well. So you do have to install the JDBC connection for SQL Server on your Hadoop machine in order to do this. We tell it the name of the computer, the database we want, fairly typical connection string, my heavily encrypted password there, as you can see. We tell it what table in Hive that we're actually wanting to talk to, and we tell it the target directory that we're looking to pull from. And this lets us, in this case, the import is actually moving data from the SQL Server side to the Hadoop side, and then we can actually export to go in the opposite direction. And let me just see if... Okay, so it did actually time out again because for whatever reason my computers have decided they're not visible to each other. I will see if this does show it. So one of the things you'll notice here is when we initially ran this, you saw some references to MapReduce. Behind the scenes, all Sqoop does is basically look at the metadata on the SQL Server side. It looks at the metadata in the Hadoop file system, and it basically builds some MapReduce jobs to handle the copying of the data over. So Sqoop is great for kind of a quick hit on this. It tends to be slower than the other options, so not necessarily what I would recommend if you're doing really high volume, regularly scheduled data loads. But if you're looking to just quickly move some data and it's kind of a one-off thing, Sqoop is perfectly adequate for that. So, okay. Now let's switch back and we'll take a quick look at Pig. Pig is basically, as I mentioned, data transformation inside the Hadoop environment. Pig and Hive actually started off kind of as competing solutions to the same problem in the Hadoop world, which is MapReduce code is really hard to write. It's up till just recently, you had to do the coding in Java to write MapReduce jobs. And the Microsoft's actually extended that recently to support .NET as well on their HDInsight distro, and I believe you can do it on the Hortonworks distribution as well. But it's definitely a newer development. So to write a MapReduce job, you had to be a Java developer. They really were looking for how do we make this easier for people who aren't already programmers to interact with data that's in Hadoop. So Hive and Pig basically were two different solutions to that. This happens all the time in the open source world where two different groups come up with different ideas and approaches and build their own products to do it. They do take very different approaches. So Hive, as we saw, uses more traditional SQL syntax. You can do select star from to actually retrieve value. Pig uses a language that is fairly easily readable, but you'll notice it's definitely not SQL. The idea behind this is that it makes it easier to do the processing, to read the information, and the newer language gives some more flexibility in how things are structured. So one of the things with Pig is, by default, it does not have direct access to SQL Server. It does have plugins to let you connect to other things, but right now you typically wouldn't use it to pull from SQL Server or to write directly to your SQL Server. However, it is really good at producing text that you can then use an SSIS package to pick up the information and move it to your SQL Server or vice versa. So if you want to produce a text file and then BCP that into your SQL Server, that's certainly an option using Pig. One of the reasons you might want to do that over using SSIS to produce the text file, Pig has the ability, because again it compiles down to MapReduce, to spread the processing over every node in a cluster. So if you have a very large job that's going to run on terabytes plus of files in your Hadoop file system, then SSIS doesn't really have a way to say, hey, I want to do the processing of this spread across all these different nodes. Pig has that baked in, so it will automatically figure that out. So it can run much faster and in a much more parallel way than SSIS can. So let's take a quick look at what Pig looks like. So basically, the syntax here, we have you can look at this as being a variable or an alias is the term that they use. But I'm basically defining, I have something here called source, and source is equal to load this data. This is referencing an HDFS directory. And I want to read the information in that directory using Pig storage. Pig storage is that plug-in point that I was talking about. So you can actually plug into other things. Pig storage is the default, and it knows how to read basically default files within the Hadoop file system. I am using the pipe symbol as a delimiter for my files, so I actually have to override the default there. And then if I want to, I don't actually have to do this in Pig, but I can actually define, when I read this and you see those pipe delimiters, these are the names of the columns that I expect to be returned. Notice though that I don't have any data type information on here, and it's because for this processing I don't really care about the data type. Pig can infer data types. If I tell it I want to do an aggregation operation like a sum, it's going to infer that the data type involved must be a numeric data type, and it will throw warnings if things don't meet that criteria when it's actually reading the data. But for the most part, it's a lot looser than SSIS is as far as data types go. So I've defined this placeholder for source, and then I can do additional things to that. So I can filter the source value by arrival at 8 minutes greater than 0. I can then group those things together. So this gives me kind of a procedural approach. And you know, if you're used to data movement, this is actually fairly readable to understand what's going on here. So I'm actually not going to run through this entire script because we don't have that much time. But I am going to run just a couple of samples. So, oh, you know, I just realized what was wrong with my demo. Apologies. Let me so my apologies. The Hadoop system wasn't set to automatically start, and because I rebooted, I forgot to go in and run that when I first started. Unfortunately, by the time this gets done, we'll probably be about out of time for the presentation. So I'll let this start up. We can switch back, and if we have any questions, it'll be ready for me to jump back and show it. So that gives you kind of a quick sample of what Pig looks like. And again, not as commonly used if you need to get the data directly to SQL Server, but if you need to do a lot of heavy-duty processing on the data in Hive, particularly to take advantage of the data in the HDFS file system, particularly if you want to take advantage of the parallel nature of it, Pig is a great option for that. So, a couple of other options you can use here. You can use Hive and the ODBC driver to create a link server in SQL. I'm not a huge fan of this option because link servers traditionally have a few problems, particularly around performance. You can easily run a query via your link server that ends up returning just a tremendous amount of data on the Hive, from the Hive instance, because things, certain filtering can't actually be pushed through to that link server. It's not able to optimize that the same way it could if it knew the link server is a SQL server on the other side, as an example. So you can end up creating some really poorly performing things using that approach. But it's there, particularly if you just need to occasionally run some simple queries against your Hive system. Text, always a great option. HDFS loves text, so anytime you want to save something out to a text file and then move it to into your Hadoop file system, or reverse the process, write something out to text and import it into SQL, that works great. As already mentioned, because you can go to text so easily, a pretty good option ends up being BCP. So you can actually just write the text file out and use BCP to bulk insert it, and that works pretty well in a lot of situations. So some quick resources on this. I'll actually leave this slide up as we start looking to see if we have any questions. But HD Insight is Microsoft's distribution of Hadoop. This is primarily designed to run in the cloud using their Azure storage. They do have an on-prem version, but it's a little bit out of date. Hortonworks, I should have their link up here. I apologize for that. Hortonworks has a distribution called HDP 1.3 for Windows, and that is a version that is designed to run on a Windows server platform. And then SSIS, if you're more interested in getting more data on Sqoop and Pig, then just sqoop.apache.org or pig.apache.org. And then you can always reach out to me on either Twitter or via my email address. So, all right, let's just see if we have any questions coming in.
We do have a few, John.
Rachel, do we have any questions?
Yeah, we do. So the first one is, can we use SQL 2005 and SQL 2008 SSIS for Hive?
It gets a little bit more complicated there. The reason being that the ODBC connections and sources and destinations are new for 2012. In SSIS 2005, you have to use the ADO.NET provider and map that through to the ADO.NET ODBC source that then you point to the Hive data source. So I haven't tested it myself, but I don't know of any reason why it wouldn't work doing that. But well, actually, I can think of one reason. If the ODBC driver you're using to access Hive doesn't implement all of the required interfaces that the ADO.NET provider expects. So I haven't tested it, so it should work, but your mileage may vary.
Okay, great. Our next question is, who are the end users of big data?
That's a fantastic question, and it varies. So business analysts, tend to use the results of big data. They don't necessarily query big data directly. There's a category that you may have heard called data scientist that's been promoted pretty recently, and this is the definition of a data scientist varies on almost a daily basis, but the definition that I've liked best out of the ones I've heard so far is it's a combination of a person who understands the data, understands statistical analysis of data, and also understands business problems really well. And they'll typically go in and use kind of advanced statistical processes to look at these large volumes of data and identify patterns and useful pieces of information for the business out of it. So that's one of the people who are more likely to directly be interacting with it. Outside of that, companies use this for identifying patterns for things like Amazon's market basket recommendations. So we all are consumers of big data. If you browse the Amazon website to a certain extent, That's more of a behind-the-scenes usage of it. So.
Okay, great. Our next question is, does this transfer work for Hadoop on Windows as well? Does it matter?
The transfer should work. So if I'd had all my services up and running when we actually started this presentation, you would have seen it actually transfer from a Windows server running SQL Server 2012 and SSIS on that box to a Windows Server 2012 running the Hortonworks Hadoop distribution. So it will work successfully between a Windows machine to a Hadoop instance on a Windows machine. It also works against Hadoop on a Linux distribution. So it should work pretty much seamlessly regardless of what platforms you're using.
Okay, great. How will SSIS handle unstructured data with multiple delimiters?
Okay, so that's a fantastic question. The way this works, you tell Hadoop when you read the information out how to handle that data. So as an example, let's see if I can go back over to this, and if my machine's up, we might actually be able to see this a little bit better. Just test my connection. Hopefully everything started okay. Yeah, this is taking a really long time. Let me see if I can get this open. Hey, it validated. Great. And now it won't open. So one of the things that you'll see when we do this, we look at our columns. If it will let me look at our columns. I'm sorry, I don't know why my machine's running so slow. So this is the columns it's expecting to get from the Hive table. And I'm going to actually go in and we can look at the metadata. So basically, the ODBC driver is handling some of the conversion to try to make its best guess. You'll notice all the strings are 255. That's because Hive doesn't actually define string lengths when you define a table. A string is just a string. So the ODBC driver lets you set some defaults. If you have heavily structured data that has multiple delimiters in it, it really depends on how you query the information out of the Hive system. So Hive has some extensions onto your standard SQL syntax so that when you're selecting, if you're selecting from an array column, that's an actual data type in Hive, you can say, I want the 5th element of the array as part of your select statement. And then you'll get back a metadata type in the ODBC driver that reflects whatever the defined type is for the array elements. If you want to do things, if you don't do that, if you just reference the column as a whole, and you don't reference a specific element, it will basically return the values of that column directly back. So you'll see a string with whatever delimiters are present in that particular column to enforce the separation of the array elements. So you do have to be somewhat careful with that. One of the nice things, again, about Hive is you can actually code your SQL statements to handle parsing out those elements so you get nicely defined specific types back.
Okay, great. And our last question is, can we use big data for reporting like SSRS and Crystal?
Yes, you should be able to via the ODBC driver. So you can already, I haven't used SSRS or Crystal against it personally. I know you can pull the information in via Excel against the ODBC driver. I have done that personally. And again, as long as the select syntax that you're using complies with Hive, you should be able to use SSRS running against an ODBC driver against a Hive database to query information.
Okay, great. Thank you so much, Sean. And as always, everyone, the session was recorded and it will be posted on our website by the end of the week. So if you missed any part of it, please check back by the end of the week and it should be up on our Learning Center. And